Welcome to lecture 11 on module 5 for the subject ARM microcontroller and embedded systems. The subject code is 15EC or 17EC62. So in the previous lecture, we discussed about task synchronization and one of the issues in task synchronization, which is the racing condition. So we shall discuss the next synchronization issue, that is what happens if there is no task synchronization whenever the resources are being shared. Okay, so this is the second type of issue that may arise. So this issue is known as deadlock. So what is a deadlock? So it is a condition in which a process is waiting for a resource held by another process which is waiting for a resource held by the first process. Okay, so simple example here. Process A, it has, see, holds means it has the access to a resource X. So it already has the uh, access to resource X, but process A, to complete or to continue its operation, it also wants one more resource, which is resource Y. So please remember, process A has only access to X, but it wants the access to Y, but it doesn't have the access to Y, but it wants the access to Y. But process B, in the other way, what it has is, process B has the access to resource Y. It already has the access to resource Y, but to continue its operation, it needs the access to process X. It needs the access, but it does not have the access. Okay, so a simple scenario is, okay. So let's say there is a two-wheeler in your house. Okay, there is a two-wheeler in your house. You and your brother want to use the two-wheeler to go somewhere. Okay, so now it is a, let's say, race among you two, so to get the access of the two-wheeler. Okay, so in that process what you do is, so the first, let's say, the first brother, he has the access to the keys of the two-wheeler. Okay, he has the access to the keys to the two-wheeler, but for the two-wheeler to run, he needs the petrol. Okay, so there is a shared resource here. Fine. So two persons, let's say P1 and P2. P1 and P2 want to access some shared resource. Okay, to access that shared resource, you need two things. What are the two things? In this case, it is a two-wheeler you want to access. Okay, so for the two-wheeler, to access two-wheeler, you need to have the key for the two-wheeler, and to use it or to start it, you need the petrol also for the two-wheeler. So let's say person one, he has the keys. Okay, he has the keys of the two-wheeler, but he doesn't have the petrol. Okay, to start the two-wheeler. So in the other case, this person two, he has the petrol. Okay, he has the petrol, but he doesn't have the key. But he wants the key, but he doesn't have the key. Getting this? This is what is a deadlock. So for starting the two-wheeler, okay, for starting the two-wheeler, a person or a process. So let's say the process are P1 and P2. They, to start the two-wheeler, this P1 should have the access to both the resource, the key as well as petrol. Okay, so whenever it has the access to both key and petrol, then only it can start the two-wheeler. Same case is with the other process also, P2. But what has happened here is, P1 has the keys but it doesn't has the petrol. P2 has the petrol but it doesn't have the keys. So in a simple way, you can say that both the processes doesn't have what it is required to start the two-wheeler. So P1 has one resource, but it wants the other resource, so that once it acquires the other resource, it can start the two-wheeler. Same is the case with P2. So it has one resource, but it wants the other resource. So if you say this resource is X and this resource is Y, so I'll mark it with a different color so that it is easy. So there is no, yeah. So let's say if this is the resource X and this is the resource Y, so in P1 has X but P1 wants Y. So P2 has Y and P2 wants X. So each process depend on the other process for the shared resource. Okay, so that is what will happen here. So deadlock is a condition in which a process is waiting for a resource held by another process. So in this case, process A wants Y, which is held by process B. Okay, for a resource held by the first process. So and process B is waiting for a resource which is held by process A. So it is a circle. Okay, you can say it is a circle. Process B wants X. Okay, but X is with A, and process A wants Y, but Y is with B. So neither processes can complete their operation, okay, in this scenario. So that is why it is known as a deadlock. Okay, so deadlock means there will be no progress. Why? Because process A is not willing to give off X. Okay, why? Because it already has X, it wants Y to complete. So it says, why should I give away X, okay, without acquiring Y? So that is what it says. And same case is with process B. It already has Y. It says it will not give away Y until it gets X. So neither process can continue. Okay. In this case, to avoid this, what has to be done is, if you come to this petrol and key example, so what has to be done is P1 and P2, they have to communicate with each other, saying that, okay, so P1 request P2, give me the petrol, I already have the key, so I'll use the two-wheeler, and once I come back, I'll give the keys and the petrol back to you so that you can use the two-wheeler. So this is what should happen. So process A holds a resource X and it wants Y, held by process B, and process B is currently holding Y and it wants the resource X, which is currently held by process A. So both hold the respective resource and they compete each other for the other resource. So hence neither of the processes can complete or progress. Okay, so this is one more scenario wherein, so at a traffic junction, so if there is no traffic light, so if there are no traffic lights, so cars will progress or will enter the junction from all the four sides, and at the center what will happen is there will be traffic jam. So once traffic jam will happen, so neither of the four cars can progress, okay, because there is a jam. So and behind this car there will be more cars, and behind this car there will be more cars, and behind this car again there will be more cars, and behind this car again there will be more cars. So neither of the cars can progress if there is no signal. So signal means in this case there is no task synchronization procedure. Okay, if there is no task synchronization procedure. So what are the various conditions that favor the deadlock? That is, what are the conditions which will help to form a deadlock? Okay, which will lead to a deadlock. First one is mutual exclusion. So if mutual exclusion is not there, that will favor the formation of deadlock. So what is this? The criteria that only one process can hold a resource at a time. This is the criteria of mutual exclusion. Mutual exclusion says that whenever there is a shared resource, only one process or task is given the access to that shared resource. So the other task or processes should wait. They should not be given simultaneous access. That is what is mutual exclusion. If mutual exclusion is not followed, it will lead to deadlock. So meaning process should access shared resource with mutual exclusion. Typical example is accessing of display device in an embedded system. So next thing or next you can say criteria that will favor deadlock is hold and wait. Hold and wait means that is what has happened here. Okay, so hold and wait is what is happening here. So process A holds X and it wants Y. So it will hold X and it will wait for Y. And process B will hold Y and it will wait for X. So hold and wait. This should not be there. Hold and wait should not be there. So if it is there, it will favor the deadlock. So hold and wait, the condition in which a process holds a shared resource, okay, and waits for additional resources. So this should not happen. So if a process gets the access to all the resources it wants, then only it should be able to continue. Otherwise, if it is trying to hold, if it has some resources and if it is waiting for some other resources, then automatically the process should be taken away from all the resources. Okay, it should not be allowed to hold some resources and wait for some other resource. That should not happen. So automatically it should be taken away from all the resources so that this condition fails. This condition doesn't fail, it will support deadlock. So next is no resource preemption. This is one more condition. If there is no resource preemption, it will favor deadlock. So, what is what do you mean by no resource preemption? Is so an operating system cannot take back a resource from a process which is currently holding it. Okay, so again, if you go back to this example, see if this would have never been this would have never happened if the OS had a permission of resource preemption. What is that? So if the OS had the you can say permission to take away resource X from A, so then what would have happened is process A would have already have Y. Since X was taken away from A, so the X is free now. So X could have been given to process B, so that process B will get X as well as Y and it can continue its operation. Okay, so this is possible only if the OS has the permission to take away the resource from a process forcefully whenever it wants. If this is not allowed, it will it will help to form the deadlock. So next is circular wait. The process is waiting for a resource which is currently held by another process. So that is what we discussed. So all these conditions were first described by a person known as E.G. Kaufman in 1971, and these conditions are known as Kaufman conditions. So circular wait, no resource preemption, hold and wait, and mutual exclusion. These conditions which favor the deadlocks, they are also known as Kaufman conditions. So how will you handle deadlock? So once deadlocks are formed, how to handle them? So a very simple method is ignore them. Okay, so there is a saying that ignorance is bliss, right? So just ignore it. What do you mean by ignore? So always assume that the system is deadlock free. So very simple way to handle deadlocks. So ignore them. So uh, in some point of time it may resolve itself. The deadlock may resolve itself. Okay, so it is just an assumption. That's all. So Unix is a OS which follows the criteria of ignoring deadlocks. So it is not bothered about them. Okay. See, it is said that whenever someone or some person is bothering you, so the best way you can do is ignore that person. Then the other person who is bothering you, so he himself will set set himself up. Okay, so that is what will happen. The second method of overcoming deadlocks is detect and recover. Detect and recover, so the name itself indicates. First, you should be able to detect a deadlock. Once you detect it, then only you can recover from the deadlock. So suggest detection and recovery from it. So once a deadlock traffic jam is, so example is, I said the example is taken as traffic jam. So once the traffic jam is detected at the junction, the only solution is, what is the only solution? Back up the vehicles from one direction and allow the vehicles from opposite direction. If I go back here, so once the traffic jam is formed in this junction, the only way you can remove the traffic jam is, so let's say you back up all the vehicles in this lane. So back up means move the vehicles back. Okay, so you have to move the vehicles back in this lane. So move them back so that this lane can proceed. Okay, so you have to move all the vehicles in this lane to move them back so that this lane becomes, at least you can clear the traffic in this lane. Okay, so this is known as backup vehicle technique. That is what is the second technique. Okay? Prevent, detect and uh, detect and recover. So back up the vehicles from one direction and allow the vehicles from other direction. So the problem is, if the traffic is very high, lot of vehicles may have to be backed up. Okay, so this is known as backup cars technique. So next is avoid deadlocks. So how to avoid deadlocks? Careful resource allocation techniques. So that is the way of avoiding the deadlocks. So one example is install a traffic light mechanism. So or install a task synchronization mechanism. Okay, which will let's say prevent the deadlocks, which will prevent the task synchronization issues. And next is the last way of avoiding the deadlocks is, sorry, to come out of the deadlock is prevent the deadlocks. So how will you prevent the deadlocks? Simple. You have to remove these conditions. So you should not allow circular wait. You should not allow. You should not allow no resource preemption condition. That is, a OS should be allowed to preempt a process and take away the resource forcefully. So you should not allow hold and wait, and you should not, or you should allow mutual exclusion. Okay, so that is what the last way of coming out of the deadlock. Prevent deadlocks. So by negating one of the four conditions, which is the four conditions we discussed, Kaufman conditions. So next, in the next lecture, we'll talk about task synchronization mechanisms. Okay. So what are the various mechanisms that are used for task synchronization?